So in Seebeck effect, we saw that there must be a temperature difference, and there is a hot junction temperature and a cold junction temperature, and the wires, the metal wires should be different. So a thermocouple can therefore only measure temperature differences between the two junctions, a fact which dictates how a practical thermocouple can be utilized. Please note here that the voltage which are obtained on the other end, that is the cold junction, are in millivolts. So their range is in millivolts. This is a typical example. Here the hot junction we have 100 degrees C, and the wires are iron and constantan. So at cold junction what we are getting around 4.5 or 5 millivolts, 4.5 millivolts around here, which we will read that is equivalent to 80 degrees C according to the chart. So this is a chart, standard thermocouple alloy conductor combinations. There are these are the different ports for the thermocouples, and then their combination, the material with which these are made, and their temperature ranges. For example, in gas turbine STT-400, N-type thermocouples are used in the combustion chambers to measure the temperature, where the temperature is around 1215 Fahrenheit. So this N-type thermocouple is used there. Now this is a chart where we have the temperature on the x-axis and millivolts on the y-axis, and for the different thermocouples we have this chart. We can read through the millivolts. If we are supposed for K-type thermocouple, if we are reading 50 millivolts at the cold junction, then there would be around 1250 degrees C temperature going on. So this, please also note that the characteristics are not perfectly linear. These are linear, but to some extent, but not perfectly linear. Now this is all about thermocouples, their basics, and now we talk about the RTDs. RTDs stand for resistance temperature detectors. These operate under the principle that electrical resistance of certain metals increases and decreases a repeatable and predictable manner with the temperature change. So if the resistance increases with the temperature, we say that this is the positive temperature coefficient, and if the resistance decreases with the increase in temperature, we say that this is the negative temperature coefficient. And this is a simple example of construction, its dimensions of a simple RTD. RTD is these three normally configurations in which the RTD is usually made: wire wound element, inner coil element, and thin film element. RTD lead wire configuration. So this is a very important information that in industry 2 wire, 3 wire and 4 wires RTDs are used. Now the difference is the extra wires, 3 wire and 4 wire, these are compensation wires. We know that when two resistances are connected in parallel, the net resistance decreases. So these are that's why these are known as compensation wires, to reduce the overall lead resistance, so that the actual resistance effect of the element RTD can only be considered. So for a 2 wire should only be used with very short runs of lead wire, no compensation for lead wire's resistance. So there should not be so much distance, otherwise the resistance effect of the leads will be involved. For a 3 wire, most commonly used for industrial applications lead wire, we have the color coding as white, red, red. And for a 4 wire, we have which are in laboratory, which are used in laboratory, which were used historically in laboratory, but nowadays in industry, in temperature transmitters like Rosemount and other transmitters, we have seen that the 4 wire RTDs are normally used. So 4 wire RTD, we have 2 compensation wires, and their color coding is as white, white and red, red. Wheatstone bridge. So this is a Wheatstone bridge. RTD is normally used in Wheatstone bridge. Wheatstone bridge uh, in a Wheatstone bridge, actually, if the bridge is balanced, then there is no flow of current through this ammeter. So if the ratio R1 over R3 is equal to R2 over R4, we will get no voltage here. This is due to the basically voltage division rule. Here we have the supply voltage, and if the two resistance ratios are equal, the R1 over R3 and R2 over R4, if this ratio is equal, we will get equal voltages here, and the difference between these 2 points will be 0, no flow of current. However, if there is difference in the temperature, and due to the change in temperature, if there is change in this resistance R4 RTD, then there will be some voltage potential difference between these 2 points, and current will flow. So this Wheatstone bridge is the most common method for measuring the resistance of an RTD is to use a Wheatstone bridge circuit. In a Wheatstone bridge, electrical excitation current is passed through the bridge, and the bridge output current is an indication of the RTD resistance. The most common material is platinum for the RTDs, and normally it is used as PT-100, which means that its resistance is 100 ohm at 0 degree C, and its resistance at 100 Celsius is 138.5. Hence the fundamental interval of 38.5 ohm per degree C. So this should be calculated accordingly. If we measure the resistance, we can translate and check that what temperature would be. There are other materials available for more unusual temperature ranges, such as germanium, which is 100 to 100 degree Kelvin.